running that version of the Linux kernel there, 2626, and it's a Monte Vista distribution. They do some real-time Linux kernels. And essentially, you can just plug in your USB thumb drive to the side thing, which is normally used for viewing music and viewing pictures. But instead, you can actually just flash a new firmware onto the TV, completely, either DOSing the TV to make it very hard to recover from, or I don't know. I'm sure you can think of some pretty clever things you could permanently write to the frame buffer on your friend's TV. Alternately, you can just plug in the serial back and pop out a root shell if you have the time for that. So while these attacks aren't that sexy, you have to be at your friend's house and wait for you until it goes to the bathroom to ruin his TV. A lot of the newer models are coming with Ethernet and Wi-Fi, which just makes them another network-connected Linux box, which of course will probably have the worst patch management ever, since you don't think LG has a full-time kernel team working to push out security updates for these devices. And lastly, which I think is the most important reason that you should care about Linux kernel security, is that memory corruption is boring. I don't mean to offend all of you guys in the audience, but it's getting hard. And doesn't mean we shouldn't work on it because it's hard, but if you have a modern Linux distribution with all of your protections, NX, SLR, PIE, RELRO with canaries, exploiting that is going to be very difficult. And there's a lot of non-traditional memory corruption vulnerabilities that are pretty interesting in their exploitation vectors. We've seen, it's not only kernel space. There's some in user space. Like I thought the UDEV Vuln from last year was pretty awesome in terms of the various creative methods you could use to exploit it. There were some straightforward ones, but there were ones that were a lot more fun. But in general, there tends to be a lot more of these non-traditional vulnerabilities in kernel space than there does in user space, simply due to the complexity of the various subsystems of the kernel. And it might require you to actually know a significant amount about a particular subsystem, which makes for at least an engaging vulndev experience, but at the same time, these aren't the same sort of exploit patterns that you're going to apply over and over to like you would with a certain class of bugs. So it's interesting, but at the same time, it might not be as reusable as some exploitation techniques. But if we actually look at some of the local privilege escalations in the past year or so, over 60% of them were not traditional stack and memory corruption vulnerabilities. So a lot of the serious bugs in the Linux kernel do fall into this category of these logic bugs or these non-traditional vulnerabilities that we think are pretty interesting. So if we put it out on the scale of cyber war to cyber Pompeii, I guess you could say, I would rank kernel vulnerabilities definitely above user space vulnerabilities and just slightly above squirrels. I hope Hoff isn't here because he will kill me if he is. No, that's good. I probably butchered his poem too. So before we go forward talking about some of the vulnerability classes in the Linux kernel, it helps to go back and see where we've been in say the past 10 years because that seemed like a good number. So if we look at the number of vulnerabilities in the Linux kernel dating back to 2000 to 2009, we see that they are significant in their quantity. Looking, you can see some anomalies in 2005. There was a big spike around there. Actually, in 2005 was the first release of 2005 was the 2611 kernel, and it was when developers and also security researchers really started switching over to 2.6 and adopting and started looking at it a lot closer. It's when they started the new stable versioning scheme where you have a minor and a micro version number x.y after 2.6. But the security gods are not without irony. Linus's announcement email for 2611 said it's now officially all bug-free, which if you look at the graph, obviously it was very bug-riddled as opposed to bug-free. But it's more interesting to actually break this down into the severity of these vulnerabilities since not all vulnerabilities are created equal. And we can see that the spike in 2005, even 2006 a little bit, was mostly low severity vulnerabilities as scored by the CVSS scores in NVD and CVE databases. And more importantly, we see that in 2008 and 2009, we see this growing number of high severity vulnerabilities, which are really the ones you mostly care about. Sure, there might be local denial of service vulnerabilities where an unprivileged user can crash your system, but really that's only going to affect you if you have untrusted users that are just heckling you, maybe in a university setting. And also, the common response is, well, kernels get bigger over time. They have a bigger attack surface, and they grow in code size. So of course, if there's more code, there's going to be more vulnerabilities. So we can actually normalize these vulnerabilities by the number of lines of code added to the kernel over these years. And we see that even when they are normalized, 2009 was still definitely the worst year of Linux security. So the Pwnie award was not unfounded and was not based solely on Linus's rants. Of course, it's important to compare to other operating systems too, just to ground ourselves. We see that Linux kernel does have a good number of vulnerabilities, but how are other operating systems doing? How is kernel security going in a broader sense? If you look at these other operating systems like Windows or OS X, their kernel bugs are pretty small and dominated compared to the Linux bugs, both in the medium ones for 2009 and the high severity ones for 2009. And that, of course, makes for a very, very sad operating system. And even worse, it means that the Linux kernel averaged over 2 vulnerabilities a week for all of 2009. So when we're talking about these devices, especially embedded devices, that are going to have fairly difficult QA and patch management cycles, 2 vulnerabilities a week is a lot for a company who doesn't specialize in Linux development to keep up with all these patches. So we're going to move on to some of the vulnerability classes in the Linux kernel. Of course, most exploits can be broken down into both remote exploits and local exploits. Remote ones are fairly rare, but there are some exceptions, and they tend to be very spectacular exceptions. Recently, last year, there was the SCTP Houdini exploit from Skuraku, which was pretty cool. It was SCTP is a transport protocol similar to bounces out TCP and UDP features in a more flexible format. But it is not that commonly used, but it is used by telecoms frequently. So if you did have an SCTP server listening on your network, the SCTP stack, which was relatively new in the kernel, was vulnerable to a remote overflow and a remote compromise via a kmalloc overflow. And it's a pretty involved exploit, but you should definitely check it out because it is some great code. Also, Julian had a Mad Wi-Fi one a couple years back, which is a wireless driver for Linux, which is also pretty neat. It was a stack smashing attack. One thing that's interesting about these remote attacks is you essentially have 2 exploitation contexts in the Linux kernel. Your exploit's either coming from locally, which means it's probably going to be in a syscall handler, where a local application makes a call into the kernel to process some application, and there's vulnerable routines in that particular kernel handler. Or it's going to be coming remotely from a hardware interrupt-based context, which is most of the time these remote exploits where you'll have a device driver receiving an incoming packet and processing it somehow and causing corruption. So actually going from a interrupt context and sort of stepping down into a actual syscall context and getting a shell to spawn back is a pretty complex issue. And those exploits have some pretty cool techniques for dealing with that. Of course, the ones we're going to be mostly concerned about are local exploits, since they tend to be quite common, and they mostly are in the form of privilege escalation, although we'll discuss some potential memory disclosures as well, which can aid in other attacks. And these local exploits are generally the cause of this large attack surface that the kernel has. If you think of a kernel, you might just think of, okay, there's a syscall interface, and all the kernel does is abstract away the hardware from user space. But in actuality, there's a whole lot of different areas that are commonly exploited by attackers. If we look around the circle here, these are probably the most common areas. You have your traditional system calls, which tend to be these passing data back and forth. IO cuddles are set and get socket options, where parameters to these might not be sanitized, so you can either send a lot of memory or copy a lot of memory into kernel space and have it overflow buffer, or you can actually get a lot of memory from an unsanitized length and have it leaked back to user space. A more interesting area is the memory management subsystem, which we'll talk about a little bit later, where we can actually desynchronize what the memory management system thinks is the state of the physical memory and page table entries from what they actually are, thereby